In this video, we'll be talking about absolute and conditional convergence, which are two different ways to talk about convergence of series when they don't contain only positive terms. So we dealt with how to handle series that all have positive terms. Now we want to go beyond that to deal with series that don't all have positive terms, because this will become super important when we go on to more general things in future videos. So we need to be able to handle whether these series converge or diverge, and what that looks like for the case of not all terms being positive. So our first definition here is that of absolute convergence. So we say the series converges absolutely if the series, where I take absolute value of every term, converges. And this here is now a series of positive terms, so the methods that we had before for dealing with those series apply for determining if a series like this converges absolutely, because now the resulting series does only have positive terms. So as a couple examples of this, we want to look at this series sum from 2 to infinity of -1 to the n over n to the fourth, and -1 to the n minus 1 over n. So if we look at this first one, I want to know, does this converge absolutely? So to do that, I have to look at the related series, sum n equals 2 to infinity of the -1 to the n over n to the fourth, with absolute values on it. What happens with the absolute values? Well, that -1 to the n is always either 1 or -1. So in absolute value, it's always equal to 1. So that's going to become a 1. And since n is positive, the end of the fourth is not going to change. So this is equal to the sum n from 2 to infinity of 1 over n to the fourth. And that we know converges by p-series. So therefore, this series over here, -1 to the n over n to the fourth, converges absolutely. For the second series, we have sum n from 1 to infinity, -1 to the n minus 1 over n. So to look if this converges absolutely, I have to take the absolute value of the terms inside, giving me the sum n from 1 to infinity of -1 to the n minus 1 over n, absolute value. Again, the absolute value gets rid of the -1 to the n term because it makes it all just 1. And then the n is always positive, so that stays. Sum n from 1 to infinity of 1 over n. And this we know diverges by p-series. So what that means is that this original series of -1 to the n minus 1 over n does not converge absolutely. Now this doesn't mean that it diverges, that doesn't mean that it does not converge in general, it just means it does not converge absolutely, which is a certain type of convergence that we do not have for this second series, but we have for the first one. Now why is absolute convergence useful? Well, the statement here sort of gives us the point of that. Said a different way, this theorem says if a series converges absolutely, then it converges. That is, it tells us that absolute convergence is a stronger condition than just convergence. So if I can prove that something converges absolutely, I then know for free that it converges. Why does this sort of result make sense? So we have the two series, some absolute value of an and some an. If the one on the left converges, that means the rectangles, when they're all added up in the same direction, are going to 0 fast enough to force convergence. So that means if I take some and make them negative, right, the only difference between absolute value of an and an is that some terms might be negative. If I take some of those rectangles and make them negative instead of adding them, well, I've made the sum smaller in that case. So I can't get divergence if I know that my rectangles are going to go to 0 to force convergence anyway. Making some positive and some negative can't make this diverge. So that's conceptually, from a more mathematical point of view, what we really have is that I can bound an between absolute value of an and negative absolute value of an. If I add the absolute value of an to all these terms, 0 is less equal to an plus absolute an is less equal twice absolute an. Since we're assuming that an converges absolutely, this series will converge. And so by direct comparison, this one also converges. Then I can subtract off the one I know converges to give me that an also converges by itself. So in either case, the proof there isn't really that important. The important idea is, if I know a series converges absolutely, then I know it converges and I can use that as a fact. However, that's not the only way to get convergence for a series that has positive and negative terms. What this said was that if it converges absolutely, then it converges. It could still converge without converging absolutely. And that's what this definition gives us, the idea of conditional convergence. The infinite series converges conditionally if the series converges, but the series is not absolutely convergent. So conditional means I know for a fact that my series itself converges, but the absolute value one diverges. This means a series cannot both converge conditionally and absolutely. Right? Conditional convergence depends on the series not converging absolutely. So you cannot have both of these at the same time. And this part here is very hard. The idea of how do I show that a series converges conditionally is a very tricky concept. So we'll be doing a lot to develop a specific method we can use to figure out that a series converges conditionally. There are a lot of ways out there that you can use to show that a series converge conditionally, but we'll only go through one in this class, only one that's in the scope of this class. And that's the alternating series, which we'll talk about in future videos. So the idea here is just what does it mean to absolutely converge? It means that a series of absolute values converges. And what does it mean to converge conditionally? It means that the series itself converges, but the absolute value series diverges. And so this only works for series that don't have all positive terms. If a series has positive terms, the two series above, the series itself and the series of absolute values are the same series, so they can't have different results. This gives our first sort of idea as to what might be different with series that don't all have positive terms, and we'll see in future videos what we can do with this to actually talk about them converging.